We're cool, good. Nobody's totally okay. 28 people. I always look at these as if they're as if these are like the exact datas, but I also see 28 people have voted. 58 people in the room, so over half the class is not voted. I know some of them are TLs and such, but even still, a lot. And I mean, maybe the 10 or 20 people who didn't vote are all in the super hard, totally lost bucket. So I don't know. I don't even know what I can take from this. I guess I can see that at least three people think it's very easy. Three are easy-ish, which is I can see the semblances of a bell curve here, right? We have this tail and this tail, but this one is conspicuously empty. I'm sure that okay, this is if we imagine this is a bell curve, right? We there's a conspicuously empty tail at the back of this, and I don't know. I'm not going to take this data to say that nobody is lost, but I will say that those of you who are feeling lost, make sure we're not. I don't want you. I don't want to leave you behind. But I do want to say that it is up to you if you are totally lost to take responsibility for that. And I'm not okay. That sounded harsh. What I want to say is that you should, if you're really lost with graphs or with the traversals or with reading these problems, understanding these problems, or with the data structures and algorithms, or with Python or whatever it is, it's up to you. Now it's up to your TL too, right? Your TL's job is to help us figure that out and help you talk through that, help answer your questions, help you come up with good questions if you're stuck with that. But ultimately, you need to figure out what is it that has me lost, and how do I get myself at least from a 1 to a 2, right? So it's okay. This is difficult. This is absolutely difficult, and I think that this is probably okay. There's no right answer, but I do think that this is the goal, right? This is our goal. I want to have not so many people in totally lost. Difficult, but I sort of understand is I think a good place to be. And as many people who are threes, fours, and fives, of course. But yeah. Try to get, if you're in this bucket, in this one bucket, try to think of the questions. Okay, and that's some people. Some people will say, I don't really learn that well in this format. It's like I need people to give me more direction than this sort of like what we do in CS, where we give you a framework to solve your problems and expect you to figure out the solution based on that framework, right? We get feedback that says like, I don't really learn in that abstract way. I just need I need more hands-on direction. Again, this is sort of as if that's how you feel. It is a very, very important skill for you to be able to ask those questions, right? To be able to say, this is what I need. How can I get, but like, you're not going to have in your job a boss who comes to you and spends an hour walking you through the assignment you need to do, right? So you need to learn how to get that in as short and as concise and as directed a way as possible. So that's, if you're totally lost, that's where I would focus my energy on getting those questions, on getting from yourself from a 1 to a 2. And I think that's in education, it's called metacognition or psychology, where it's like knowing, it's not just like expecting yourself to be taught, it's knowing how you learn best and setting yourself up in those situations. If you're in a situation where you're not taught like that, then how can you get what you need? How can you get the knowledge that you need in order to make sure you learn it? Because you're the one who needs that knowledge, right? Who needs those skills, so you can get those high paying software engineering jobs. Whatever, we're here to support you however we can. But I think, again, one of the challenges of remote is that we don't have direct eyes. Like, I can't see your faces, right? I can't see who's totally lost and scratching their heads and confused. We have these polls, but the polls, we had 37. We're getting a more accurate number, but still, right? I think it's we all have to work together, including on your end, to make sure that you let us know what's needed, and we'll try to provide as much guidance as we can. Yeah, I think graphs are fundamentally super simple. Yes, they're simple, but they all have the same big picture, but the details are complicated, and the details are where you're going to get caught up, and the details are what's that's something you kind of have to figure out on your own, right? Like we can teach you the big picture ideas, but your fingers need to actually type out that code. You need to name your own variables. You need to come up with your own plans and organize your own code, right? That's something that we can't really teach. Like we can give you hints, we can give you help, but ultimately you just got to put in those reps as far as like the implementation. And that is, yeah, I agree. And you're going to see with the maze traversal, the concept is going to be similar to all of these problems we've gone through before, but it has a lot of little details, and if you're not careful with those details, you're gonna find yourself in a big tangle of spaghetti code. If you have the nice thing is if you have a good handle on the big picture ideas, that does let you focus on the details, like coming up with good variable names, like writing easily readable code, like keeping a train of thoughts. But if you don't understand the problem, if you're not coming up with a good plan and executing based on that plan, there's so many places you can get hung up. Like with the island counting problems, right? If you get one index wrong, or if you forget one boundary, or if you get an X and a Y mixed up, the whole thing can all fall apart, and it can be sometimes hard to figure out where it is. But that's also why I think these are good problems. Even if you think like, oh, I'm not going to do backend, I don't need to know this stuff, right? Maybe you're doing data visualization. Those come with graphs too. Data analysis, things like that. So, and in general, anytime you're writing a more complex algorithm, these things, all of these techniques, these repetitions that you're putting in will help you succeed. Yeah. Okay. If you're here and you understand the problem, but you can't code the solutions on your own, practice. Go to LeetCode, go to HackerRank, and start on the easy problems. Go back to your old homeworks and just like maybe you had to use Google. Go back to Intro to Python. Remember those things. Do a list comprehension that will print all of the names capital. Do a list comprehension that will print the names of all of the people who are above age 32. Right? Go through those things and solve it without Google, right? Maybe you had to Google it the first time, understandable since you just learned Python like one day ago. Try it without Google now. If you can do those, try building bubble sort, try building insertion sort, try building a linked list. Go through all of these things again. If you had to use Google the first time, if you had to have help, if you had to pair program, if you had to work closely with your TL to get you through that, now try it on your own. You should have that in your head. Start from the basic building blocks. And if you can do a linked list traversal, you can do a binary search tree traversal. It's only instead of one pointer, you have 2 pointers. That's the only thing. If you can do a binary search tree traversal, you can do a general tree traversal. It's the same thing, except instead of 2 pointers, you have an arbitrary number of pointers. And if you can do a tree traversal, you can do a graph traversal. That's all you need to do is keep track of the visited nodes and ignore nodes that have already been visited. Right? There's each of these building blocks. And I mean, this is one of the cool things about Polya is it encourages you to go back and figure out which of those blocks that is missing. And then, you just start from there. Especially now that we're approaching the end of curriculum and you're not going to have, someone waking up every morning at 9 a.m. to teach you new concepts. And you're not going to have a TL who's on your case. Hey, did you do your thing? Did you do your thing? You didn't show up for stand-up. Like, where are you? Like, talk to me. You're going to have to be more self-motivated. Now there's eternity of material on the internet, in training kits, so many resources that are available to you. But with that metacognition, with that experience of learning how you learn best, this is you're going to be using those skills. You're going to be using these problem-solving skills to tackle problems outside of the context of Lambda School. And that's what you're going to need to succeed in your jobs. And that's what the interviews and the job recruiters and all of that are going to be looking for as well. Again, use these last few weeks you have, use them wisely. We're giving you a complicated problem. Use this as a challenge to challenge your problem solving skills, right? Can you solve this? What are you missing? Get that understanding about yourself, and you'll do very well. Okay, cool. This is the HackerRank one, right? Yeah, math. I think some people just have blockers when it comes to math problems. Some people are very strong in math. That's something we're trying to figure out, because it's true that I mean, computers are basically big calculators, so you don't need to do any calculations usually, right? But there is still some math involved when it comes to things like, all right, we want to create 10 users with an average of 2 friends each. You're going to need to do a little bit of math to figure that out. Now, it's not it's not, I mean, it's not the most complicated math, but I will say I do know, and this is what I did before Lambda School, is I was focused on early education. A lot of people fall off like in 3rd grade. Like, oh, I got 90% on my multiplication test, and I thought I was good at math. Then I got to long division, and I was just terrible. And from then on, like, I just never got math. I think that's unfortunate, and I think that's hard to, if that was your experience in school, it's really hard to talk about even things like this. But I will say, even with that, like, it's not too late. If you have an adult mind, metacognition, you're aware how you learn, you can absolutely go back and review stuff like fractions, like long division, algebra. Like, this is just algebra basically. Big O is just algebra. If a 9th grader can handle it, even if you think and you've thought this for the last 30 years that you're not good at math, you can absolutely handle it. So these are again good things to think about when you're the one directing your own education. Yeah, and I think this is a good challenge too. Like, you want it to be fun. Like, for example, when I took linear algebra in college, I failed it. Like, I literally failed it. Like, I got a flat F minus on the test. I just didn't. I didn't get linear algebra. But then I got to computer graphics, and computer graphics uses a lot of linear algebra. But I actually liked computer graphics, and I think it's because I like video games, I like animation, things like that. Okay, now I get it. And it's the same calculations that I just failed. But when it was in a context that I could appreciate, actually, I became pretty good at it, and I was pretty good at computer graphics as well. So sometimes it is just finding that right project to like spark it, right? Maybe you hate graphs, but maybe, oh wait, building a social network is something that excites you. And maybe that can be your gateway into exploring graphs in a practical setting. Okay, but that's a good transition to get us back into our problem. So when we last left off, we built we were on step 2 of our 3 steps to solve any graph problem. Again, steps 1 was understand the problem, translate all the terminology into graphs terminology. Step 2 is to build the graph. We built our graph here, and we built a specific kind of graph, which was a randomly generated or procedurally generated, if you like, a randomly generated social network. By that, I mean that we wanted to create some number of users with an average of some number of friends each. This seemed to work pretty well. We came up with an n-squared solution that is, whoa, hold on. Here we go. Here it is. Here was our n-squared solution. So where the n-squared came from, we have this line. This is going to be an O of n, just a simple for loop for each number of users. We create a user. Standard O of n. Here we have a for loop and a for loop. Standard O of n squared. Then we shuffle. Now, shuffle is O of n, but in this case, our n is n squared, right? So this is actually also n squared, because our possible friendships is n squared. And then we sliced off this number of friendships, from the top of the list. We divided it by 2 because we know that every time we call add friendship, it actually creates 2 friendships. And we created all of those friendships. Again, it works perfectly fine. It's O of n squared, which is not too big of a deal when we're working with numbers as small as like 10 or 10 and 2. So that's okay. That's okay. Our next task here was to implement the degrees of separation. Now, when we looked at the top of our problem spec, we saw that we're building this social network. We got this requirement, this technical requirement from our PM, our project manager, to say that in our social network, we want these rules. We want you to only be able to see the profiles of the people in your extended social network. An extended social network is means someone who is connected through any number of friendship connections. We translated this in step 1 to say extended social network is the same as connected components, right? Connecting through any number of friends means that we have some amount of friends in common, which we can tell through either a breadth first search or a depth first search. We want to find, okay, so we have that. We want to also be able to see for every user the shortest friendship path between each. So I guess if we wanted to look at like user 1, how they connect to user 2, we can see that user 1 up here, this is our social network. User 1 is not friends with user 2, but they both have a friend in common. They actually have 2 friends in common, user 10 and user 5. So our path from user 2 is 1, 10, and 2. Presumably, we could also say 1, 5, and 2, but since they're the same length, it doesn't matter for our spec. We translated in step 1 as well. Shortest friendship path is going to be the same as breadth first search. So with that, if we understand this, if we look at this, okay, we can see what about from user 1 to user 7? It's going to be 1, 10, 2, 7. So 1, they're friends with user 10. User 10 is friends with user 2, and user 2 is friends with user 7. So that looks good. And okay, it seems like it makes sense because user 7 only has 1 friend. That's user 2. So it does seem like we have the same path to 2, and then just the 7 on top of it. Okay, so I think we understand this problem pretty well. I think we left at a good spot. So let's get into the code. Now, all of this that we've done, this is basically step 1 of Polya, right? As I've repeated, and I know no one believes me when I first say it, but hopefully as we've gone through some more of these problems, I'm starting to convince you. When I say step 1 is almost always going to be the hardest step. And if you're having trouble with step 2 and step 3, it's usually because of some misunderstanding, some misinformation, something missing from step 1. So all of that was step 1. Now, if we understand all of that, if we understand the problem, we can start to come up with a plan. Okay, so what's our plan? Put another way, can somebody please describe their algorithm to get all social paths in a sentence or 2? Move this so we can see the problem up here. Maybe I'll move this to the bottom. Okay, BFS of requested user for all that haven't been seen. Okay, that's a sentence fragment. But okay, I think I get what you're saying here. Iterate through each friendship and perform a BFS from the initial user ID through that individual friendship. Return the path, return the visited dictionary. Traverse connections to each friend, adding paths to each as you go until you find all reachable friends. Sorry, I saw you delete it. I'm not criticizing. Thank you for being the first one to type it and send it to break the awkward ice. But look, it was okay. that could be a first pass. You can always iterate and make it clearer. Okay. Sounds like we're generally on a similar, we're generally on the same page. So we want to look at each friend, right? We want to look at each friend. We know we're going to have to perform a BFS because BFS will give us the shortest path, whereas a DFS might give us a valid path, but that might not be the shortest. What else? We want to store it in a dictionary. Okay, this is interesting. We said dictionary, not a set, right? Before we were using a set. I think this is good because even though they're both hash tables underneath the hood, now instead of using a set which just stores the keys, we can have keys and values, so we can get the same. I I see. It's actually just given here. So maybe that insight was came from this. But yes, I think that would work. I think there was also a hint about that, right? You can use a dictionary. Okay, so that's I guess points for reading the problem and reading the hints. That's an important part of this. But I think that sounds like it'll work. Okay. Create an undirected graph of user and friends. So we have that. Perform a BFS. We have that from populate graph. I mean, actually, yes. Perform a BFS search with the user ID as a starting index and friends as the destination vertex. Yes, and then we need to do that for every friend, right? For every friend that's reachable. What if there's what if we have someone with no friends? There's a question I have for you. Like here, what if we were doing this graph? User 2 has no friends. So what does that mean? What does that mean? How do we get the social path from user 1 to user 2? Introduce the that's one way to do it. That's one way to do it. Yes, they won't have one. They won't have one. So user 1 should not be able to view user 2's profile, right? By the definition of our spec, our social network will wall them off. Maybe he can see them in the list, but they should not be able to view each other's profiles. Okay, and you also cannot see a social path because the social path will not exist. So that's perfectly fine. That's getting back to connected components, right? We know that a breadth first search is guaranteed. Breadth first traversal, I should say. A breadth first traversal is guaranteed to visit every single node that is reachable. Okay, so I like that. I like that plan. I think we're on a good track. So some key things were like for each. Let's see. Do a BFS. BFS or BFT? BFT or BFS? BFT. Like we're kind of doing a BFT because if we're doing connected components, we're doing a traversal, right? Connected components, you do a traversal, and everywhere you've reached that's how you find your connected components. Search is like if you're searching for a node. So search is to get a path, right? But we're also kind of doing I would say this is more of a traversal than a search. Like we're not searching for any single thing in particular. So I'm going to call this a BFT. Let's say, but store the paths as we go. Or do a BFT, store the paths as we go. This seems good. Do a BFT, store the paths as we go. When we reach an unvisited node, add the path to visited dictionary. And then return visited dictionary at the end, right? So here is our plan. I think this should work. So we're just going to do a BFT, but we want to store the paths as we go. When our BFT finishes, we can return our visited dictionary. And when we reach an unvisited node, add a path to the visited dictionary. Okay, so this is our plan. Note that there are some details that I left out, right? Like that every time we visited a node, we need to add it to the, okay, I guess we didn't miss that. I didn't put, for example, create a visit dictionary. I didn't say create a queue, right? That's kind of captured in this do a BFT, but we could break this down even further. We could copy paste our BFT code from there and our plan. But I think this is enough for us to start coding. I think this is enough to start coding. This structure is important because this structure is what's going to keep our solution organized. It means that even if one part is broken, that maybe our whole program does not need to be broken. Okay, so let's start writing the code. Do we have a queue up here? Do we have a stack, or we might need to copy that? So let's copy a queue for our BFT. Throw this up here. So to do a BFT, we Q equals Q. Maybe I can write this down. Create an empty queue. Add a path to the starting node to the queue. While the queue is not empty, dequeue the first path from the queue. Check if it's been visited. If not, mark it as visited. And then I can copy this because this is what we mean by mark it as visited, right? And then add a path to each neighbor to the back of the queue. And then at the end, we return our visit dictionary. So this is our algorithm. This is our BFS algorithm, our BFT algorithm with a little bit of path storage built in. So here's our plan. Now I think we should be able to just write our code. So Q equals Q, visited equals this. Move this down here. Add a path to the starting node to the queue. So Q.NQ. Our starting node is going to be user ID. User ID. While the queue is not empty, while Q.size is greater than 0, dequeue the first path. So path equals Q.dequeue. We want to get the vertex. I didn't write that out, but this is similar to our previous one. Equals path -1. Again, our vertex is going to be the last item in our path. Check if it's been visited. If v not in visited. Now, even though this is a dictionary, we know that the in will check the keys. So this will work just like a set. With the underlying hash table, we get this for O of 1. So it's very efficient. If not, we mark it as visited by, replace this one with this. When we reach an unvisited node, add the path to the visited dictionary. So now we can say visited of v equals our path, right? And we remember, so we know this is a path to the vertex from the starting node. We also know that this is not in, v is not in visited, so we know we're not going to be overwriting anything. This is important because if we've reached it already, that'll be the shortest path. And every path we look afterwards is going to be either the same length or longer. So we don't want to overwrite any shorter paths. Now we do add a path to each neighbor to the back of the queue. For neighbor, we can actually say for a friend, right? Because we know these are friends. For friends in self.friendships of v. Maybe in v we could call this like ID, but just to keep it similar to our last one. For friend in self.friendships v, path copy equals path.copy, or you can do list of path. Path copy dot append friend. Maybe we can call this friend ID. Friend ID, and then q.nq path copy. Return visited dictionary. Return visited. Is that all? Is that all? Okay, I'm gonna try to run this and see if it works. Okay, am I not in the right one? Not in this one. Here we go, social. Python 3, social. Okay, so we have our users, we have our friendships. I'm not printing out the social paths, so let's do this. Print social paths. Okay, so let's see. Does this work? Were we defining friend ID? Friend ID is defined in this for loop. And we know that this is self.friendships. So this is our adjacency list. So this is going to be a list of all of our friends, right? So here's our adjacency list. So user 1 is friends with user 8, user 3, user 7. User 2 is friends with user 10 and user 6. So that's what this friendships is. So when we're saying for friend ID and self.friendships, like for user 1, that's going to return this. So we do number 8, we do number 3, we do number 7. Okay. Do a BFS for each other person in the network. Yeah, that's I think, Jack, this is true. And then we're just not going to reach like the loners. Like user 11 has no friends, so we would never reach him, right? But I think that would lead to some redundancy, like we're calculating some paths redundantly. Not that I wasn't thinking about that, but I think that this will be more optimal. Okay, so let's see if this works. User 1. Okay, I think we're pretty confident that this works, right? What was our goal? 11 users with an average of 3 friends each. I'm not counting it all, but this looks about right. This looks like about 3 users per friend. So user 1 is friends with user 8, user 3, user 7. Yep, we have 1, 1. We have 1 to 8. Yep, and 1 to 3 and 1 to 7. So these are all the users. The social path is user 1 is actually friends with these 3 users. User 4, user 1 is not friends with user 4, but it seems like they're both friends with user 8. So user 8, yep, user 8 is friends with user 4 and user 1. That's correct. User 4 is friends with user 8 and not user 1. Okay, so that looks good too. User 6, 1, 8, 6, 1 to 8, 8 to 6, yes. Same with user 9. 8 is friends with 9, and same with user 10. 1, 8 is 10. So user 8 is quite the social butterfly. User 5, we go 1, 3, 5. Yep, that looks good. User 2, 1, 8, 6, 2. 1, 8, 6. Where's 6? Here's 6. And 2. Yep, so that looks good. So there's a lot of people that are not in our network. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so actually there's only one person who's not in our network. That's user 11, because user 11 does not have any friends. So that makes sense. So it seems like our social paths are working pretty well. Again, our BFS, or our BFT, if you will, the algorithm is almost exactly the same, right? Memorize the algorithm. Don't memorize the code. The code it'll have so many little nuances and little differences. And if you're just remembering blindly, you're going to get those wrong. But if you memorize the algorithm itself, like, okay, first we create a queue. We need to keep track of our visited nodes. Add the starting node to the queue, and then while the queue is not empty, check if it's been visited. If not, mark it as visited, then add all of its neighbors to the back of the queue. That's something that I actually think is really helpful to memorize, just because A, it's a pretty simple algorithm, and B, it takes so many shapes and forms that you also don't want to have to spend too much mental energy doing the code, right? Just remember, okay, I need to build the graph and then traverse it. Traversal will be the easiest part if you've memorized this. If you haven't memorized it, it might be the hardest part. But for these problems, traversals almost always look very similar. Try it with a graph of 18 users and 5 connections. Sure, let's give that a shot. 18 and 5. Okay, so here's our 18 users. Here's our social paths. Let's just pick one at random. Let's see to 13. 1, 3, 13. 1, 3, not friends with 13. Good. User 3 is friends with 13, so that looks good. What about 15? 1, 18, 15, 1, 18, yes, and 18 is friends with 15, yes. So looks like looks like it's doing pretty well. Okay, this takes us to, now that we have this running, and this is kind of the cool thing about about procedural generation, is that if you can do it for small numbers, you can do it at large numbers. This is something that maybe some of you discovered when you were doing your procedurally generated Lambda MUDs, where if you make a generator that can generate 10 rooms, it's actually not too much more to generate 100 rooms. If you can generate 100 rooms, you can generate 1,000 rooms. You can generate 10,000 rooms. You can generate 1,000,000 rooms. All that's limiting you is your processor speed and your processor power. But the same code should work for any of them. We can actually try that out by doing something like what we want to create 1,000 users with an average of 5 friends each. All right, so let's try testing at scale, right? This works for 10 users, works for 18 users. What about 1,000 users with an average of 5 friendships each? 1,000. Let's try running it. Okay, it took a little bit while, like still less than a second, but this is our social network. Okay, there's a lot of friends. I don't even think that I can verify this, but it looks good to me. It looks good to me so far. I don't. Yeah, I don't even want to check this, but I trust that it works. I mean, maybe we could do some small testing to see is this a valid path or not. But I'm curious. Does anybody have an answer to this problem? Did anyone come up with an answer to number 2? And if you did, I'm curious how you came up with this problem. Okay, yes. You ran it a few times. It was always over 99% with an average connections around 5.5. That's a average of 4.5 degrees of separation with 99%. Yes. Okay, yes, this is awesome. This is awesome. This is exactly what I was hoping you would do. Now, sometimes people can get hung up trying to calculate it mathematically. Now, I'm sure you could do this. I'm sure there's some formula. Actually, I think students have found it. There are formulas to calculate like the average degrees of separation. I think Facebook has published some papers on this. Like who is in whose social network, or like LinkedIn, or like there's a Kevin Bacon thing, right? I said we would get back to Kevin Bacon. This is the 6 degrees of Kevin Bacon. Almost every actor or actress in Hollywood is connected to Kevin Bacon through 6 or less connections. Now you could calculate it, or you could run it, and if you run it, these are the kind of numbers that you'll see. Yes, even though we have 1,000 users with an average of only 5 random friends each, that means you're friends with less than 1% of all users. You're friends with less than 1%. Yet you are still in the extended social network of 99% of all other users. Now, who are the people who are not in there? Probably our outliers who just have no friends, or you might have like a little island where each person only has like 1 friend and they're on their own little island. You also might get unlucky, and maybe your user 1 is on an island, and your user 1 has no friends, in which case you're going to get 0%. But those edge cases are usually discarded, and then we talk about averages. So this is also what I mean by you don't have to be that good at math, in terms of you don't actually have to calculate this, but you do want to be able to set up something like this, something like Ang just posted, where okay, this is my calculator, right? I need to know how to set it up in order to do the calculation I want. I don't actually want to calculate it myself. I'm just going to run it a few times, and because computers can run it really fast, you could actually run this 1,000 times and take the average of 1,000 runs, and that's a pretty good estimate. Big O is great. Big O is very useful. Big O can help you think about things when it's impractical to actually test. But if you can test, and testing is actually not as hard, like testing at scale, I should say, is not as hard as you might think. If you can do things like procedural generation, again, if you can make it so builds 10 users, it can build 100 users. If it builds 100 users, you can build 1,000. You can build 10,000. You could build 100,000. So those are that's how you might scale test a social network. We went through this one again, but this is the thing where you have to divide by 2. So it'll be like 10 times 100 divided by 2. So this is 500. Which loop is this, Sean? Your for loop is on the same. For this one. For this one. Okay, so you hit MVP, but this is also a good time to. Okay, so if it works for 100, 1,000, this is assuming you have like an O of n, right? Because what I said is not true if you have like an O of n squared, or an O of n cubed, or an O of n factorial. Then if it may work for 100, but it will absolutely take like 100 years to return for n equals 10,000. So that's where data structures come in. That's why like we use a visited hash table instead of an array. Like if this was an array, let's see how much longer it would take. Visit. Oh, actually we can't do this because this is we need key value. But it would take a lot longer because we're checking for we're doing this call much more often. So that's I guess that's where things like data structures and algorithms come in. That's where step 4 of Polya comes in, where you go back and you iterate on your solution, you do analysis, and then you think, hey, this is an O of n. Can we speed this up to an O of 1, or maybe an O of log n, using a data structure, or perhaps using a sorting algorithm, or something like that. Okay. Some of these stretch goals, you might have found the results from question 2 to be surprising. I know that I found this a little bit surprising. Again, you're friends with less than 1% of all users, yet you're still connected to 99% of users in the social network. That's kind of surprising. That actually, would you expect results like that in real life? For example, if you had a real life, maybe Lambda School is actually a really good example of this, right? We have more than 1,000, but let's say Lambda School is 1,000 people. And you have probably about 5 friends, right? Like, you know a lot of people, but you have your good 5 friends. Maybe that was your labs team. Maybe you're really good friends with your TL. Maybe the people you started your cohort with, you've been moving, right? I would say it's reasonable to say that people have an average of 5 friends in Lambda School. Would you expect to see results like this, like in real life? In terms of like, let's just say 5. Let's just say 99% connections with an average of 5 degrees of separation between each. Put another way, like, is our random distribution a good model of real life friendships? I mean, it's better than just non-random, but is it a good model? Yes, exactly. Yes, this is correct. The friendships, like in real life, friendships are not totally random. Like, you are localized. You will be friends with the people in your cohort, or the people in your track, or like you probably don't have that many friends in CS16 or something, or in like web. What are we on? Like web 27. You probably don't know anyone in web 27 unless it's like a friend who you encourage to apply. But you are more likely to have friends in web. What is this? Web 23 or iOS? I don't know what numbers other people are on, but yes, it's not exactly going to be purely random. How would you improve this? This is a bigger question too. We're not going to totally go into this, but these are other things you can explore in terms of procedural generation. Things like Voronoi. Okay, yeah, like things like this, like these. This is sort of, I think someone brought this up after Build Week. But this is like a way of making random distributions in a more organized way, right? You can see that, okay, now people kind of set up in like their own geographic locations and cluster around certain things. This is like how flowers, like in a flower field, flowers will grow in this area. This is a more natural and organic way of distributing things. So if you need to, and like I would say, unless there's a need, you probably don't need to do this. If you're just doing testing, like stress testing or scale testing, that random is probably fine. This will get you the edge cases of like users who have 0 friends or users who have a ton of friends and things like that. And it'll get you pretty good numbers in terms of like what is the average number of friendships for some number of user. Like that's probably, these are probably roughly accurate. Like maybe in Lambda School, an actual social network, you would find that you're still connected to 95% of people, but through an average degree of like 7 or 8 instead of 5. So like, is it important to get really accurate numbers? Maybe. But that's you don't want to optimize unless you need to. Optimize to make it faster or optimize to make it more accurate. That's sort of what step 4 of Polya is. You look at your results, you say, are these good? Can we move on, or do we need to iterate and make it better? Even if it's not 100% optimal, in real life, you have deadlines and you have a million other things to do. So a lot of times you'll say, all right, nothing's broken. May need to come back to this, but for now, we can leave it. Okay, Adam. So you're in that. So you're in the network too. You're a 2nd degree Kevin Bacon connection. Okay. Last thing on this before we take a break is I want to talk through this solution. I'll let you think about it, and then we'll go through it after our break. So did anyone get to number 2? Did anyone come up with an O of n solution for populate graph? Again, populate graph was the problem we went through yesterday, and we determined that it was n squared because of this block right here. So is anyone able to get an O of n solution? Okay, sorry, I missed this one. For yesterday's homework, could we have just imported the BFS function and utilized it that way? You can import it, but you'll have to change a couple of things, right? Like you'll need to change the visited from a set to a dictionary. You'll need to, I mean, this is the same. You'll need to figure out what the get neighbors is, right? Instead of, so you'll need to change it to friendships. But overall, you could do that. If you understood what the differences are. Yeah, totally. But I feel like it might be more. It's easier to just memorize the algorithm and then fill in the code as you go along. But I just know when I copy paste and then try to adjust the copy pastes, I always miss things. And you see me do that too. Sometimes I do that with guided projects, and I'm like, what? I don't know what's going on. But if you actually follow Polya and do it from the plan to the comments to the code, things usually end up going smoother. This is a lot of TLs tell me, yeah, like I know you said Polya, and when I was a student, I never really listened, But now that I'm like doing this again, and now that I'm working with students, like I can see, oh, I should have just been doing this the whole time, and it makes sense. And I totally understand that as well. I know it takes some time to sink in, which is why we all repeat it 10 million times. Me, Beej, Brian, everyone. We hope that all this repetition will help it stick in your head, and one day you will see the wisdom in the words. Okay, let's see. Peter had this algorithm for I in range 1 to 11. Oh, is that regarding this? Did anyone have an O of n solution? I don't think this is the same. Yeah, so Peter, I think this will work, but you're just doing some redundant searches here, right? Because like if you're going to, what's a graph we can look at? If you're going from like, if this was our social network, for example, you're doing like A to B, right? Okay, but then you're going A, B, C. So you're doing that A to B traversal again. Then A, B, D, and then A, B, D, F, and A, B, C, E, and A, B, D, G. So you're going from A to B so many times. Whereas if you just did it in one step, you would just do that traversal once. So that would be fine. That's fine for small numbers, but if you want to, if you're testing at scale, which we are, we're going to be playing with, it will you're going to run into some trouble. And it sounds like you did, right? Or no, it sounds like Sean did. Um, oh yeah, this is also hard coding only 10 users. Yes, that's also true. That is also true. Um, okay. So nobody. I'm actually surprised because when you were all thinking about your problems, or when I asked you your plan about to solve this the first time, the meaning yesterday when we went through this, many of you, maybe just a handful, but many people were actually thinking along the lines of the O of N solution. Okay. If nobody came up with it, let's take our 10-minute break now because when we come back, we'll go through this and we'll weigh the differences, we'll weigh the trade-offs because as you'll see, this O of N does not come for free. Um, but we'll examine those trade-offs and see when it's appropriate to use, when it's not. You might have seen the hints up here that our second topic for the day is random sampling. So that should be a hint for you as well. But let's take our 10 and we'll come back and get into that. All right, see you in 10. All right. That was 10 minutes. Come on back. The colors of, yeah, those blocks. I'm planning to take those out, or at least change them. Those were just an experiment. Also, this song, I don't know. I think you could hear it. I think I shared my audio. But the song was an experiment too. That's something I did with a couple of my friends during a music hackathon. And if you haven't done a music hackathon before, it's a lot of fun. It's just like a coding hackathon. Yeah, you get together with like teams of like 3 or 4. Everybody gets a prompt. It's like a group thing. You go off in a studio, you record a song based on that prompt. You start at like 10 in the morning, you go to like 4 in the afternoon. And then you all listen to each other. We got like tacos, and we all listen to each other's interpretation of the prompt. So that was our hackathon. That was one of the most fun things I've ever done on the oboe. So I think it's a cool idea, and if you all are interested, I think it's pretty easy to run as well. Yeah, there's a Nijabe's oboe song that I like, even though that's played by Yusef Latif, who is not a very good oboe player. I mean, he's a good musician, but I think he plays like 20 instruments, and I don't think that makes the best oboe. But Nijabe's is awesome. Music is fine too. For one of these hackathons, I decided I wanted to sing. You know, I'm tired of playing the oboe. I want to sing. So I actually wrote some rap lyrics, and I did a hackathon where I rapped. Our prompt was like snowy tumble or something like that. So that was fun. Like these are like I think I played so much classical music, so serious, right? So regimented that I needed some place to stretch, and that's where these hackathons came through. But yeah, no, I don't have a budget for this. The Tetris song from before, I actually hired someone to do. So that was cool. But still, like I haven't totally figured out like the look and feel. Um, but anyway, oh, I can show you, as I promised before. We talked about social graphs and social networks, and you may be thinking like, this is all well and good. This is all fine in Python, but I'm not going to be, even if you're doing Django, right? It's not going to be vanilla Python. How can I use this for my real? Can this be applied to if I were to build a real life social network? The answer is yes. So okay, my menus again. This is not totally working, but I mean, this is an actual social network. This is my local development, so it's not. It works, but the flower mechanic is broken. But I can show you like the back end and how it's actually structured. So here's my console, my Ruby on Rails console. Where am I? Oh, friendship. Friendship is this model. I can show you the Ruby code, which even though maybe you don't know Ruby, but you can still probably understand this, especially if you're a full stack web. So here's my model. Here's my model. Again, those of you who know Django, who did Django, it's going to be similar to this. This is my friendship model. Okay, the fields are not here. The fields are here. So it has an ID, has a user ID and the friend ID. This is the pointer, right? The user ID is going to be the user, and then the friend ID is who it's pointing to. This is very similar to an adjacency list, except instead of storing it in a dictionary, we're storing it in a relational database. If you wanted to do something like get all friends, get all friendships, you would do a query. Since this is a one-to-many relationship, or a many-to-many relationship. Many users can have many friends. This is a one-way pointer. You can see that when we create a friendship, we're actually creating a bidirectional friendship. So we create the user ID, friend ID, but then we also create the reverse, where the friend is the user and the user itself is the friend. All right, here's our two creations. You can also get the inverse friendship. This is just something that you define to say. So if you have the forward friendship, just give me what the reverse friendship is. Then there's some additional booleans to say like, okay, an updated, confirmed, rejected, accepted. Okay, this ties to a question that I actually received just earlier this morning from CS23. It wasn't asked to me, but it was in the staff channel, so I took a look. The question was, I have an interview on system design. I have interviews on system design. How do I get better at that? The answer, like if you're looking for resources, there's a lot of good YouTube resources, but the student was looking for more resources beyond that. And my answer would be, if you want to practice system design, you have to design systems. What that means is build a social network. You'll see there's so many little details, and I have a question here. This is because I wrote this code and it worked, and then I came back and I was like, why is there a field for both accepted and rejected? Like, wouldn't accepted just be like false, or like wouldn't rejected be the same as accepted equals false? Okay, maybe there's a difference between if it's okay, I don't know, I haven't quite figured that out yet. I mean, it's not that the code is unreadable, it's just that there's a lot of details that you need to wrap your head around, and that's what system design problems are about. Not to say can you architect everything from scratch, but can you figure out, can you see the little details, and can you come up with solutions? So this was my very, very basic system design for my social network, and it works. It fundamentally works. It functionally works. Now, UI is something different. Oh man, the UI, that's like something I'm the worst at. It's also, I think that the blocks and things like that are not the most beautiful. I chose material design for my UI, just because I think it's easy. Like, you have the floating action button here. Nice. You have, Google has all these icons. You have specifications for drawers and sliders and buttons, things like that. So I use material design for the menus. But as far as things like this, I know this is ugly. What else? My achievements is super broken. Like, so that's where I struggle. But the code itself is just fine. I haven't stress tested it, but I'm pretty confident it will work. This is just this is the project I was working on. I just wanted to show you this is a real project where I like this social network we built in class. You can use the same model, the same structure, the same design to create this in real life. Like, this is a real fully functional, hosted on a server, live on the App Store app. Okay, the friendship is blocked out because it's broken right now, but the flower part is broken, not the not the friendship network. Why Ruby? Why Ruby is because I knew it. This was I built this when I was job searching. My previous job was in Ruby on Rails, and I wanted to stretch myself. So I thought, I built the front end app. I built the accounts, I built the logins, I built the high scores, I built things like that. Again, there's a lot of details. If you look at my high score model, it's there's some complexity here. My controllers are log game records controller. These are pretty ugly. These could probably be cleaned up. But yeah, the reason is because I wanted to, this is the backend I knew best. So I built a project in it. Ruby on Rails is pretty good for getting APIs up and rolling. It's very similar to Django. I think it's a little bit more, it's a little bit less free than Django. And I think that has to do with the philosophy of the language. Like, Python lets you do whatever you want, right? It lets you overwrite keywords. It lets you access private variables. Python lets you do whatever you want. And Django is kind of like that same philosophy. Batteries included, right? Just strap it on and take your rocket to the moon as fast as possible. Ruby is a little bit more strict. They say this should be here, convention over configuration. Don't repeat yourself. Ruby likes acronyms a lot. Ruby on Rails is ROR, dry, keep your code dry, COC, convention over configuration, MVC. So that's sort of the philosophy. Yeah, my real reason for using Ruby on Rails is because it's the stack that I knew best, and I wanted a project in it. That's as good a reason as I have. Yeah, again, build projects. Even a simple project, you will be so surprised how much complexity there is. Like, okay, you play a game, you get your score, and you store your high scores, right? Seems easy enough. Seems like just basic CRUD. Well, actually, there's a lot. There's a lot to it. How do you retrieve the high scores every time the user logs in, right? How do you turn? Is it an O of N operation? Because the more scores you have, the more complicated it's going to be. Maybe you can cache it. Cache costs more money. It means you have to be careful about your cache and cache invalidation. You can store it in the field itself, which is what I did. I just created a whole new table to store the high scores. Like there's a lot of complexity that comes up when you're actually getting into the details of system design, which is why I think the best way to do it is the best way to practice system design is to design systems. Plus side to that is you'll have some cool stuff in your portfolio. More projects, especially more advanced projects in your portfolio, is always going to help you. Okay, but this is this is a social network in the wild. So let's get back to our model social network, our sample social network. Right, we have the same thing, except for we're storing it all locally. We're storing them in dictionaries, on adjacency lists to be a little bit more descriptive. But where we left off, we were examining this stretch problem down here. If you follow the hints for part 1, your populate graph will run in O of n squared time. And I asked you to refactor the code to run in O of n time. Does anybody, okay, I asked this, has anybody over the last 15 minutes or so been able to think of an algorithm? And by that I mean sentences that will run in O of n time. Again, the hints that was dropped early at the beginning of class would be random sampling. Any ideas about how to solve this in O of n time? Okay. Maybe you're thinking about it, but I'm just gonna jump into it. Oh, you put one up here? During user generation, create a second array with IDs, random around average times user IDs. So you're saying if we're doing 10 users with 2 friends each, random of 20, like is around average, or is this like 2 times user IDs, shuffle the IDs after you're done, pop down repeatedly until the IDs are done, connecting neighbors in the random list, putting back copies. Okay, I think this is on the right track. I have some questions of what around average means, and what putting back copies means. Gaussian random too? Okay, you're using so Gaussian randomization. That's not going to be pure randomization then, right? Because Gaussian, I mean, I'm thinking of Gaussian blurs. Like there's a rhyme and a reason to Gaussian randomization. I think. I don't know. Maybe you're using Gaussian in a context I'm not familiar with. Okay, tends to standard distribution. I wonder, okay, this is probably my instinct when I hear this. Maybe it will work. I feel like why not just use random? And if the answer is it will only work with this specific randomization, I feel like that might get complicated. If this were a whiteboard, I would say give it a shot, give it a try. But I feel like there's a simpler. You're on the right track. But I think you can be much simpler than that. Okay, yeah, so it is deterministic. So that's sort of getting to this one, right? That's sort of getting to this one. But ignoring that, we're just going to straight random distribution. We just want to get it down to O of n time. Okay, let's just figure this out here. I'll just go through what my proposed solution is, and then we'll do some testing to see if it's really faster. Okay, so here we're going to do the same thing, right? We still want to create n users, so this can stay exactly the same. Now, what I want to do is do random sampling. What that means is if I have n users, let's say I have 100 users, I want to pick a random number between 1 and 100. Okay, that'll be my first user. Then I want to pick another random number between 1 and 100. That'll be my second user. And then I'm going to create that friendship, right? How many times do I need to do that? I need to do that this number of times. This number is the number of friendships we need to do. We need to call add friendship that many times. So we're still going to copy this. So my algorithm would be pick a random number 1 through n. pick another random number 1 through n, create friendship between those two IDs. Until you have friendships count equal to total friendships. What do you think about this? What do you think about this algorithm? So in this case, O of n, by O of n, I mean O of n meaning the total number of friendships, right? So if we're calling 10 and 20, so 10 friends, average of 2 friends each, this is going to be O of 20. If we call 1,000 users with an average of 5 friends each, this is going to be O of 5,000. Checking for duplicates is O of 1, yes. Checking for duplicates, since we are, let's see. If we try to add a friendship, if user ID equals friend ID, we get a warning. So this doesn't tell us anything, but we could easily do something like this, like return false. Return false. Else return true. So this would just say we call add friendship. If it works, we get a true. If it doesn't work, we get a false, right? So yes, this should happen in constant time. How about this one? Else if friend in self.friendships, since this is a dictionary, that's O of 1 time. Or this is also going to be O of 1 time. So yes, checking for duplicate friendships is O of 1. Then it should work. Yes, it should work. So let's see. Pick a random number, 1 through n. So we can put our target friendships up here. Total friendships equals average friendships times num users. Pick a random number, 1 through n, where n is the number of users. So user ID equals random.rand int of 1 self.last ID. This is going to be our the total number of users. We can do the same for friend. Friend ID, create friendships between those two IDs. Let's put a count here. Friendships created equals 0. Create a friendship. So let's say if self.add friendship between user ID, friend ID, then total friendships or friendships created plus equals 2. And I guess we want to do that so we can put this in a while loop, right? While friendships created is less than total friendships, we just do this. What do you think? Cycle through number of users, create number of friendships with random choice, create friendships with gotten IDs. So you mean like, I mean, that sounds like what we're doing here, right? Sort of. Anyway, let's try running this. This is called populate graph. Let's call this linear. Populate graph. Let's go back to our 10 and our 2 just to make it smaller. And we only care about our friendships. Put this populate graph, and let's do, this is our regular one. Clear this out. Wait, what are we printing? Why are we printing 2 out? Random friendships. Oh, we were not running the right. Oh, here, shuffle the list. I guess we don't need to do this. Okay, here's our social network regular. Here it is linear. I'll move this down so I don't switch around so much. So here it is linear, average of 2 friends each. It seems like this is not enough. Seems like this is not enough, right? Looks like we have an average of 1 friend each. So what's going on here? Do we miss something? Well, friendships created. Oh, because we did plus equals 2. So this should be 1. Or we can just delete this and do plus 2. Okay, so here we go. 2, 2, 3, 3, 0, 1, 3, 2. That seems pretty good. This seems like it's working, right? Okay, now which one is let's do some timing tests to see which one is actually going to be the faster one. We can run our same time. So let's go up here, imports time, scroll down here. We'll copy paste some code here. Okay, so we have social graph, starts time, num users, number of friendships. Let's start with 1005. Start time, populate graph linear. Is this what it's still called? Yep, populate graph linear. SG friendships, we don't worry about that. We run, here's our linear runtime. We reinitialize our graph. We do populate graph regular. And here's our quadratic runtime. Okay, let's save this, give it a whirl. Okay, so we got some warnings, but we can see to create 1,000 users with an average of 5 friends each, took less than 100 or a little bit more than 100th of a second, whereas quadratic runtime took almost 1 full second. So it seems like we're going faster than our quadratic. What do we do? 2,000 users, average of 10 friendships each. Let's see. Okay, so this one was in still less than 1/10 of a second, less than 1/2 of a second. Quadratic, we're getting over 3 seconds to run this. Okay, so we're you can see that our linear solution is going to be much faster than our quadratic solution for most cases. But what about this? What about this stuff? So we tried it with 2 and 5, but we started to get collisions. Now we're having more collisions. What does this mean? What does this mean? Well, do you need to check for dupes? That's what this is doing. So this is checking for dupes, right? This is when we try to create it. This will give us a warning if the friendship already exists. So actually, we can count how many collisions there are. Maybe we can suppress these for right now. But let's count our collisions. So let's say collisions equals 0, else collisions plus equals 1. Now we can say prints collisions is collisions. All right, so we run this. We can see that we had 26 collisions for our 2000 and 2010. Okay, what? So it does seem like it's faster, but what are the trade-offs? What are the trade-offs? What are the trade-offs with this implementation? Is it always going to be faster? Is there space complexity implications for either one? Is there anything we need to be aware of when it comes to this problem? There's a word or 2 words maybe that I'm looking for that we talked about at the beginning of the week that we haven't really touched on too much, but this does have some implications depending on what kind of graph you have. Put another way, if this is our graph, 2,000 users with 10 friends each, let's go back to step 1 and think, what kind of graph is this, right? We said it's an undirected graph. It's a cyclic graph. It's stored in an adjacency list. Sparse versus dense. Yes, that's the words I was looking for. Okay, what about sparse versus dense? Why does it matter if right now this is pretty sparse, right? We have 2,000 users with an average of 10 friends each, so that's pretty sparse. What if it was dense? What if it was dense? What does that mean? Well, we can think about it. We can think about it. But we could also just try it. So let's try instead of 2,100, let's try something like 2,1999. So what's going to happen here? Yes, dense will give more collisions. Dense will give more collisions. So, like, what do we think is going to happen here? First of all, what do you think? Will this affect our quadratic runtime? And how will it affect our linear runtime? Let's run it while you're thinking and typing. Tick tock, tick tock, tick tock. I don't actually know how long this will take. Hopefully my computer does not catch on fire. But you can already see it's thinking very hard. We're coming up across a lot of collisions. It will make the linear runtime longer than the quadratic runtime. Yes. Why is that? Why is that? Isn't this O of n? I thought O of n is better than n squared, right? Why is the O of n slower than our O of n squared? Quadratic will be relatively the same. Yes, I think quadratic should be the same as well, because already we're generating all of the friendships, right? So we're already generating those n squared friendships, and then we're creating them. So this is actually, if we're doing it this way with the n squared, this is going to be the optimal way, right? We're creating exactly the number of friendships we need, and then we're generating those friendships, and then we're creating them. Okay, this is taking too long. I'm going to do 1,099.99. Maybe this will return before I turn 1,000. Maybe not. Maybe not. Maybe not. What if I do 199? What if I do 199? Okay, 199, that returned. But look, we had, even with this, our quadratic runtime, now our quadratic runtime is less than a hundredth of a second, but our linear runtime is 0.14 with 38,000 collisions. That's way more. That's way more. We're only building 9,900 friendships, but we're having 39,000 collisions. All right, that's almost 4 times as many friendships as we're actually making. So what's the cutoff? I don't know what the cutoff is to where linear becomes better than quadratic, but you can see that there are some trade-offs to this. This linear runtime, yes, this is O of n, but it comes with the caveat that it only will be efficient for sparse graphs. And if you have a very dense graph, you're going to start to get collisions. And randomness can be very powerful. Randomness can turn a quadratic into an O of n, but you need to know how to use it, right? Randomness is not random when you look at it at a big enough scale. So if you be aware of this, and if you can do the math on it, or you can just try it. Like that's sort of the theme here. You can do the math, you can figure it out, you can do analysis, but it's also no replacement for good old-fashioned experimental testing. So hopefully this gave you some ideas. Hopefully this gave you a better idea of randomness, some things it can be used for, and ways to use things like big O analysis. Yeah, Brandon, if you can think of some optimizations, I think timing is also a good way to benchmark yourself. Try it for bigger and bigger numbers. Maybe if you can figure out a way to avoid the collisions while still keeping this to O of n, you might. I think those are good things to do. But also, do you what are you buying? Like, did you make it 10% faster, but 100% more unreadable by adding all these crazy optimizations? If so, I would tend to lean towards just leaving it simple like this. Like this is really simple. It's not always the most efficient, but this is pretty simple. This is also pretty simple, even if it's not the most efficient. But put together, maybe you can have something that determines if you have a sparse graph or a dense graph. And if it's sparse, it'll use this one. And if it's sparse, it'll use this one. And if it's dense, it'll use this one. That's a pretty simple optimization that will work for both types. But that's I think where coding becomes art, where there's no single best answer, and it's more up to you to use your instincts, to use your knowledge, and to use your problem-solving skills to figure out what the best solution for the given situation, for your given team, and for your given needs are. Okay, let's catch up. Yes, cool. All right, good stuff. So that's it for social network. Are there any last minute questions or thoughts, comments, ideas, anything to do with social graph before we put this down and move on to our final topic for the day? If not, let's jump into the adventure map traversal. First thing I should mention is that if you want to prepare for your sprint challenge, or if you happen to look ahead, you might have noticed that sprint challenge graphs. And if you looked ahead at your assignment, you might notice that your problem here, the problem here looks almost exactly like your problem here. In fact, they are identical, or they should be identical. I'm sure there's typos here or there between them, but these problems are identical. What does that mean? That means that this is your sprint challenge. This adventure game. So you can start on it immediately after the guided project. Take your lunch, but after that, you're free to work on this. Typical sprint challenge rules apply, so no sharing code. No, you must work on this alone. You're allowed to ask questions, but your TL may be a little bit more vague, or push you to direct you towards reading hints. Sure. You know what? This is how I like to code. I like to be hungry when I code. I think it makes me sharper. If I have like a big lunch, I get sleepy, and my mental capacities are not as sharp. So do what you got to do. But here is your sprint challenge. Okay. Why are we giving it to you? Why out of all the sprints, out of all the challenges you've done, why now are we giving this to you on Thursday? The answer is because this is a tricky one. And as I mentioned to you before, when this was in its rougher state, the first time we rolled this out was CS14, and literally 80% of the class failed the sprint challenge. This is the first time also. This was also the first sprint that we introduced MVP, which was the old name for Flex. So that was exciting. Student success had a good time dealing with 80% of the class failing. But because of that, we learned our lesson. We iterated. We added a few more hints. We added a few more tools to this, and we've also added a lot of supporting infrastructure to build up this problem. Now, because you have 24 hours on this, that doesn't mean you should procrastinate. This is a trickier problem. You will have to write a good amount of code, and it's very, very easy to while you're working on this to find yourself lost in a mess of spaghetti code. Now, what is the problem? The problem is to take this graph. We have our adventure map. You may remember this from week 1 in Intro to Python. You may remember this from week 4 in Build Week. But we have a 500-room graph, a 500-room map. And your job is to traverse the entire map. Not too bad, right? What do we mean by traverse? It means that you want to visit each room at least once. You need to set foot in each room at least once. How do you do this? you need to build a traversal path. So you start from room 0, and you walk north, now you're in this room. You walk east, now you're in this room. You walk north again, and so on. That's how you walk around, just like in the adventure game, just like in your Lambda Muds. Not like your Lambda Muds in terms of it being on a server. This is just in Python. But here's your map. Here's your graph. You may notice this may look familiar to those of you who did the room generation, but this is how we're generating rooms. We have coordinates. You don't necessarily need to use these, but it may help you when it comes to visualization. I'm going to make this big because we need a big screen for this, but let's go to this. So if we let's open this up. If we look in this code, we see we have a world code. We have some different graphs. Okay, you may uncomment some smaller graphs for development and testing purposes. We're going to load the graph into the world. Print rooms. That's nice. What does that mean? Let's try that. Python 3 AEV. Okay, we get this. We're going to have to make the screen bigger. Maybe zoom out a little bit. Okay, so here is our map. Holy moly. This looks like it could take a little while. Probably it's not going to be the most efficient to solve this by hand. But using your graph traversal methods, maybe using some graph search methods, using your knowledge of object-oriented programming, using your knowledge of traversals, of Python classes, things like that, you should have all the tools needed to traverse this path. Now we have 15 minutes left. I'm not gonna give you too many hints because A, there's some hints in the repo itself. B, this is a sprint challenge, so I want you to work on this. But with the remaining 15 minutes, I'll let you take a look at this, read through it, and see if you have any questions for me. That's again, what are the steps? Understand the problem. Come up with a plan, implement the plan, and then reflect and iterate and improve your solution. What are the tuples in the room cells for? The tuples are coordinates. The tuples are used for the visualization. Again, we built some of this in to things like build weeks in hopes that it would blunt. So you're not getting all of this stuff at once, brand new. But it's very similar, probably, to how you did your visualizations during build week. Now, we didn't tell you were working on graph problems back then, but this was all part of the plan, right? We're all building up to this, and this again is building up to the treasure hunt, which you saw in CS22's build week, their second build week. It's going to be very similar to this problem. What is all this? You can use anything you want for the traversal. Anything besides like clicking up here and looking at other people's solutions. But you can absolutely use this. You can absolutely use this. Now, does it help you? Does it help you? Maybe. Like you can find room 0. Oops. 0. Okay, room 0 is connected to room 4 to the north, 8 to the south, 1 to the east, 3 to the west. Okay, great. Now I guess I can go north and go to room 4. So now I need to find 4. Okay, now, oops, room 4 has 0 to the south. Okay, great. I traversed that path. Now what do I do? I mean, you can also use this map. Maybe you can start writing it down. I've always said this. No one has ever taken me up on it. But if you want to solve this by brute force, what I mean is saying, okay, I draw this on a paper. I have a graph paper. I say I go north to room 4. I go south. I go south, west, east, north. Okay, I've visited these 4 rooms. Now I go west, west, south. Write that down. West, south, south. Okay, write those down. Now I need to go back north, northeast, northeast. Now north, west, west, south, north, west, south, 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 and so on. You could do it manually if you want. I don't recommend that method, but if all else fails, brute force is an algorithm too. No restrictions. No restrictions. All you need to deliver is a path that will visit each of these rooms. The way it's listed in the repo, like again, these are all the same. So I mean, the sprint challenge is due tomorrow at 11 a.m. Your TL needs to know where to find it. As long as your TL can find it, I'm not picky about which one you fork. If you get the solution here, you can just copy paste your code into the sprint challenge repo. Now I think these graphs themselves should actually be the same as well. So like this map will be the same as this map. So your traversal path should work just fine in the homework as it does here. But the most important thing is that your TL knows where to find it. So whatever you want to do, just check with them. And I'm sure they'll be fine with it as long as they know where to look. What about the number of rooms? The number of rooms is 500. I can tell you that right now. There are 500 rooms. There are some smaller graphs that you can use to test out as well. If you want to see how that works, we can take a look. Like here's the basic graph. Okay. See, 0, 1, 2. We have a little hallway here. Pretty basic, right? You can also test your traversal here. So what would be our path? We're starting at room 0. How about north, north? North, north will get us done. So what if we do north, north? Or let's just do one north first. Okay, we run this test. We went from 2 unvisited rooms to 1 unvisited room. So that's progress. What do we go north again? Test passed. All right, easy. North, north passes our basic test. What if we uncomment and we do our next largest one? Okay, now we have a cross. We went north, north. So we visited these 3 rooms, but that still left these 6 rooms unvisited. So I guess we could do a brute force here again, right? Maybe do like south, south, then like south, south again. South, south. Now we want to go back up north. So hide this. Oh, hide the wrong one. Hide this. What? Wait, do you see this? Is this only me that sees a sublime text here with player high score and player high scores? I don't know what's wrong. I think Zoom is doing weird stuff in my windows. Okay, but anyway, north, north, south, 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 north, north. Now I think this should still have 4 unvisited rooms, which are the ones on the east and the west. 4 unvisited rooms. Okay, so now we just need to go west, west, east, 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 east. West, west, east, 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 and this should pass. Hey, we're ahead. What do you know? Our test passed. Okay, so this works for these smaller graphs. Again, if you want to solve the larger graph this way, I would still consider that MVP, but I would not recommend it. Better idea to start using your graph traversal skills to think about our steps. What do we mean by building the graph? What do we mean by traversing it? I mean, we have the graph up here, right? So why do we need to build it? That's something that I want you to think about. How does that relate to this problem? And there's some hints as well, so that might give you some insights. If you have 2001 moves, you do not. Oh yes. That's what I meant. Sorry, I meant number of rooms. Yes, number of moves must be less than 2,000. I will say a generally optimal path will be about 1,000 steps. So if you're over 2,000, it means you probably have some serious inefficiencies, like you're like running in circles and repeating paths and things like that. Generally, optimal path will be around 1,000. Now, getting underneath 1,000 takes quite a bit of work, but I wouldn't even worry about that for right now. Just go for the MVP of traversing the map in under 1,000. Yeah, again, if you're doing like something like a depth first traversal, you should be well under 2,000 unless you have some crazy loops going on. But if you get to 2001, if you get to 2001, you can even look through your path manually and just delete like 2 redundant steps. Like maybe if you were looking at, oh man, I made it too big. If you were, I'll zoom out. Zoom. Okay, so if you were here, right, we're in room 0. You go south, west, east, north, south. Maybe you duplicated this path: south, west, east, north. If you can detect that, you can just go into your path and delete those things right off the bat, right? So again, there's no if you need to hard code some things, if you need to brute force some things, there's no restrictions for this challenge. I'm not saying anything about how you solve it. Okay, except for, again, don't go to someone else's solution and just copy paste from their repo. Hopefully that goes without saying. But aside from that, anything that follows regular sprint challenge and Lambda School rules is all fair game. All I need is that path. All I need is that path of directions. All right. Any other questions? Questions about hints? Questions about... these are also very good. I like these kind of problems, these rubrics, because it's very clear, right? There's no ambiguity. There's no... as long as you can get this path, then you're good to go. Okay. Any other questions? Any other questions? We have 5 minutes left. I can wait 60 more seconds. See if anything else comes up. I think also that your TLs have the regularly scheduled like after hours or before hours and things like that. So I think if you're really stuck, come with good questions. I've instructed them. It's okay to give you hints, but typical sprint challenge rules apply. So no, they won't be sharing code. They will be giving more guidance than solutions. So, but there will be some support if you have questions. Would you make Lambda history if you brute force the whole thing? If you can brute force the most optimal algorithm, if you can brute force the shortest possible path, you will make Lambda history. I will tell you that the world record for this is only by one student named Chris Foster, who solved it in 917 moves, I think, which is first by far. I think that the second fastest was in like the 230s or something like that. Most students struggle to get even the best students, they get around like 950s range. This is a really optimal solution. Chris's solution of 917, that's even like beyond me, right? That's those are those wonderful moments when the students surpass the teachers, and I was very happy to see that. But my best is 957. There is plenty of ways to make Lambda history, though. We'll see some opportunities there for the treasure hunt. And those who have history in the treasure hunts, like Chris Foster, he has a shrine. He has a shrine honoring his traversal prowess on the treasure hunt server, immortalized forever. So that is there are opportunities to immortalize yourself. If you brute force the whole thing, you know what? I will be impressed. But depending on how efficient your solution is, like if you brute force like a 1,200 solution, not as impressed. But if you brute force like a 9:15, yeah, that's pretty good. All right. Well, if there are no other questions, I guess I'll let you get to your lunches 1 minute and 15 seconds early. I will see you all tomorrow at noon to go over to have an AMA session, talk about the sprint, talk about whatever else is on your mind. But other than that, good luck and see you tomorrow.